In this module, we will examine models of the different types of DC generators. These models are important in the prediction of steady-state behavior of DC generators. So these are our objectives for this module. We will explain the model of different types of DC generators and differentiate uh, their characteristics, and we'll also analyze and solve problems related to the different types of DC generators. Recall that a DC machine is made up of two parts. We have the armature circuit and the field circuit. The armature circuit is simply, or you can look at the armature circuit as a source, a DC source. So in reality, it's made up of coils that can be connected, that are connected in parallel, depending on the type of winding that it uses. So, for example, if it is a simplex, if the armature is wound as a simplex lap, the number of parallel paths there will be equal to the number of poles. If it is wound as simplex wave, it always have two parallel paths. So it is a source, but it is physically it is a coil that cut fluxes, uh, magnetic fluxes, and thus generating the voltage. Now, being a coil, it has resistance, so we call that resistance R sub A. And to extract the voltage, we have a brush, which is made of carbon, and being a carbon, it has resistance and also creates a voltage drop. So all of these components are thought to be connected in series. So the voltage that is being generated, EA, R sub A, is in series because it is inherent to the coil. V sub B, caused by the carbon brush, which is also connected in series to the coil. So thus we can model the armature circuit as this drawing. The carbon brush is modeled as a fixed source because normally, uh, regardless of what is the load of the DC generator, the drop across the brushes are usually constant. So we model it as a fixed source that is in opposite in polarity with the voltage produced by the windings. A more refined model or diagram of the armature circuit would look like this. So we replace EA, we replace the symbol of that as this symbol so that it would look like that it is produced by a rotating machine. V sub B and R sub A are still there, although they are interchanged in the drawing, but the effect of the model should just be the same as on the left side. Sometimes we don't show V sub B, especially if we ignore its effects on the circuit and simply draw it as in this manner. So here we assume that the brush contact drop is negligible. For the field circuit model, so we know that it is also a made up of coil that is wound around a pole made up of ferromagnetic material. So the model here is simply this one. So again, being a coil, uh, we show there that it has an inductance, L sub F. Um, it has a resistance. So here is the resistance of the field circuit or the uh, field coil. And normally, the field circuit will have a variable resistance connected in series with it. And therefore, the series combination of these two is what is the total resistance of the field circuit. So we call that, we label that usually as R sub F. The this field circuit is normally excited by a voltage. So this voltage could be a separate voltage or a voltage that also comes from the generator itself. Okay, so the L sub F here is the inductance of the field coil, and it is the one producing the field flux that is being cut by the armature circuit that eventually leads to the production of the voltage. So here is the um, model for a separately excited DC generator. So it is called separately excited because the excitation of the armature comes from a circuit that is separate from the armature circuit. So normally the armature circuit or the field circuit would be connected to a separate source, a DC source, okay, and a rheostat or a potentiometer is connected in series with the field circuit uh, so that the current that goes through the field circuit can be adjusted. Um, so EA there, or the voltage generated by the armature circuit, can be adjusted by varying the field circuit current I sub F because this affects the flux being produced by the field circuits. So, the field circuit is really physically isolated or separate from the armature circuit. Thus, the type of generator is called the separately excited DC generator. Now, every DC machine is usually associated with its magnetization characteristic. So, what do you mean by this? So, it is actually a plot of the internally generated voltage EA versus the field current that is fed through the field circuit. So, so normally this will be produced by running the DC machine at a constant rotational speed and vary I sub f to different values and observe the generated voltage. So that would give us this typical curve that is usually found in DC machines. So this curve has some important characteristics. So, for example, if the field current is zero, well, we would probably assume that the flux there is zero, but that's not the case. Normally, there is a what we call a residual flux on the machine, such that even if I sub f is a zero, we get a small voltage called the residual voltage. So this is usually between 0 and 10 volts, depending on how, uh, how much residual flux is left on the magnetic poles and the rotation speed of the machine. The straight line portion is uh, said to be where the voltage is increasing in proportion to the amount of current I sub f. But as we increase further I sub f, uh, it is the curve starts to flatten out. The reason being is that the field poles start to saturate, and regardless of how much you increase the current I sub f, the flux uh, would not increase that much. So therefore, it would show that the curve tends to flatten as I sub f is increased. So when you buy a DC machine, or when you acquire a DC machine, usually associated with that is its magnetization characteristics that you can use to study or predict the behavior of that machine. So this is a typical magnetization curve that was acquired at 1,800 revolutions per minute rotational speed. So the internal voltage was measured at different values of I sub f. So take note that at I sub f equals 0, there's a very small voltage there due to the residual flux. Um, well, you might ask how is E sub A determined, as it is produced internally by the windings in the armature. So this is usually done by measuring the voltage at the open terminals of the generator. So, so that voltage will be equal to the internally generated voltage at no load. So let's have an example to showcase the magnetization characteristics of a DC machine. So here we have a separately excited DC generator with a magnetization curve shown in our previous slide at 1,800 RPM. But here, the generator will be driven by the prime mover at 1,600 RPM. So the question is, what is the internal generated voltage, or your EA? If we have the voltage or the voltage impressed across the field winding is 12 volts, and the field winding resistance is 2.4 ohms. So this is the combined resistance of the winding itself and any variable resistance that may be connected. Here is the solution. So to solve the problem, we use the magnetization curve that is provided to us. So first we need to solve for the field current. So that is equals to the voltage across the the field windings divided by its resistance. So we'll get there 5 amperes. Then we look on the tables for 5 amperes of I sub F. And then um, for that amount of current, we will get, according to the curve, a voltage of 420 volts. Now, take note that this is the internally generated voltage at 1800 RPM as um, provided here by the magnetization curve, but our actual RPM as uh, dictated by our prime mover is actually 1600 RPM. So we would expect a lower voltage because remember our EA is also equals to um, the machine constant times the flux per pole and the angular velocity of the prime mover that drives the generator. So since this is 1/6, we would expect a lower EA. Now to get the actual EA, we need to do a ratio proportion to normalize our EA at 1600 RPM. So we do this uh, and that will give us a lower EA. There are several types of DC generator according to connection. So what we have cited in our example is actually a separately excited generator. This generator, the feed flux is produced by a separate circuit that is connected to a separate source. Another one is the shunt generator. So the flux is produced by connecting the field circuit to the generator itself, to the output of the generator. The third is the series generator. So the field flux is produced by a field circuit that is in series with the armature circuit. And fourth one is the a combination actually of the shunt and the series generators, where the flux is derived from two field circuits. So one is uh, the one the shunt field is one of the fields, and the other one is the series field. So they work in combination to derive a net flux that will is used to produce the voltage. Now under compound we have two types. So we have the cumulatively compounded. So in this subtype, the fluxes produced by the shunt field and the series field uh, combine uh, uh, cumulatively, so they add together to form a net flux. For the differential compounded, the shunt and the series fields, their fluxes are opposing with each other, so it produces a different characteristics for that generator. In our E106 lab, uh, these field windings are actually brought out of the module so that we are able to construct the different types of DC generator that I just mentioned. Okay, so this is our references for this module. So we have a book from Chapman. It's a fifth edition book. I know there is a newer edition, but the fifth edition will suffice. We also have a book from Fitzgerald and Kingsley. It's a more challenging. You can find more challenging exercises there and sample problems. And of course, we have fundamentals of physics that is used as a sub-reference. So that's it for the introduction of DC generators. On our next video, we will discuss deeply about separately excited DC generators.